So today we are going to discuss this topic which is called branch and bound for traveling salesperson's problem. Specifically least cost branch and bound. Least cost branch and bound. So we have three types of branch and bound technique. One is FIFO branch and bound, another one is LIFO branch and bound, and the third one is least cost branch and bound, which in short called LC branch and bound. Okay. Now traveling salesperson's problem we have discussed many times. Salesperson should visit all the cities exactly once. Meaning is very simple. Please, salesperson will visit all the cities. Let's say these are the cities, 4 cities, and whatever the name is A, B, C. First of all, we have to understand the problem statement. And all weights will be given like 7, 2, 1, whatever. It's a small thing I am showing you. 8. Okay. Salesperson will visit all the cities. So he can start from this city. If nothing is mentioned, he can start from any city. Source city. He has to reach to some destination city. And then he has to come back to his own city. Actually, he should start from the same city and he should come back. So only starting city should be repeated one time. None of the other cities should be repeated more than once. He can visit A to B and then he cannot come back to B again. Then it won't be a traveling salesperson's problem. That will be something different, which is called tour. Multiple tours are not allowed here. This is the problem statement. Now this problem statement is not solvable in polynomial time. I mentioned it many times. If number of cities, if you increase the number of cities, then in polynomial time it is not possible, but small thing we can do. Limited number of cities we can solve something. So today we are going to see branch and bound method. So branch and bound, what is the technique? Technique is very simple. It works like a breadth first search, especially for the least cost branch and bound, and whichever node will give you the, because ultimate intention is to get minimum weight. So whichever way he goes, minimum distance he should cover. That is the intention. So you can call it's a minimization problem. Salesperson will visit all the cities exactly one. He should come back to his own city, but the travel should be minimum. He should travel minimum distance. That is the catch here. Okay, and this problem is unsolvable. But anyway, small limited number of cities unsolvable in polynomial time. But for limited number of cities we can solve it. So branch and bound, how it works? Let's see. So the traveling salesperson problem, also known as TSP, asks the following question: given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once? This is the catch. And returns to the original city. So it is an NP-hard problem. NP-hard problem we will discuss next time, but remember the NP-hard problems are unsolvable in polynomial time. Polynomial time, you know what is polynomial time. What polynomial example, students? Let's say this is Fn equal to n square plus twice n plus 1. This is a polynomial, okay students? Maybe n cube also a polynomial. N to the power 4 also polynomial, but 2 to the power n is not polynomial. This is exponential. 5 to the power n is not polynomial, it is exponential. This is not polynomial, this is not polynomial. E to the power x, any time complexity is of the format of e to the power x, that is not polynomial. So normally, usually these problems are unsolvable, but every problem is on subset sum problem also. If you increase number of entries in the set, you cannot get subsets. That is also unsolvable in polynomial, but limited things we can sort it out. Okay, so this is exponential. But anyway, branch and bound, how to solve this? So branch and bound method for solving traveling salesperson's problem. Okay, so let's say given the graph is this one, which is ABCD. This is our graph. Can you generate one attendance? Okay, so ABCD is given graph. Now here the graph corresponding matrix has been given, which is ABCD. So don't just simply think that A to B is 2, B to A also will be 2. Not like that. Okay? A to B is 2, B to A is also 2. That aspect we are not considering here. It's not like simply distance, because B to E he has to visit and it may not be the same path. Anyway, whatever is there is there. And then the self visits, that means A to A, B to B, C to C and D to D, these are all infinity. Clear? Salesperson want to visit, that is infinity initially, because A to A visits, here you are assuming that he will visit all cities and come back to A. So that will be infinity initially. B to B also infinity, C to C also infinity, D to D also infinity. Now what should you do? So initial costs are given in terms of matrix. Okay, so we have to follow two major steps, because ultimate intention is to reduce the cost. Yes or no, students? This is a minimization problem. Salesperson should visit all the cities exactly once, but with limited distance. Yes or no? What are the steps we will follow? First step is that we will reduce the cost row wise. Row wise cost reduction will happen. Column wise cost reduction will happen, and then we'll add them together, row plus column, how much total cost has been reduced. Whenever we visit somewhere, we will reduce the cost of that matrix. Okay, row wise we will reduce, column wise we will. How to reduce that, then we are going to see. So initially, let's say this is my matrix given, which is just this matrix. Here I have written the matrix. Row wise I am going to reduce the cost. What you have to see? You have to see row wise what is the minimum distance that is provided. So here what is the minimum distance row wise, students? 2. 2 is the minimum in this row. Row wise, row 1, row 2, row 3, row 4. Whichever is the minimum, that we will diagnose first, and that particular number will subtract from all the elements. That means, as you said, it is 2. So 2 will be reduced from all the elements. So if you reduce 2 from infinity, doesn't matter, it will be infinity itself. If you reduce 2 from 2, it is 0. Here is the minimum value in the first row. 2. 2 only, right? What is the minimum value in this row? 2. 2 will reduce. So if you reduce 2, infinity minus 2, infinity, 2 minus 2, 0, 5 minus 2, 3, 7 minus 2, 5. Clear, students? Next row, what is the minimum? 4. Reduce 4 for all numbers. Third row, what is the minimum? 1. Reduce 1 from all numbers of row 3. Fourth row, what is the minimum? 4. Reduce 4 from all elements. So whichever is the resulting element, that you are going to write here. Row wise reduction happens. Okay, row wise. So it is 2. First time it is 2. Second time 4. Third time 1. Fourth time 4. Everything you reduced here and you subtracted it. Okay, this is row wise reduction happens. Now we have to reduce column wise. After reduction of row wise, all of you have done. Nobody is writing anything with pen paper. Done. Row wise reduction happens. Column wise also you reduce, but after the row reduction. So after the row reduction, this is the output matrix. So column wise you have to check. This is 5, this is 2, this is 1. So this one is 1 minimum. You reduce 1 from 1, it will be 0. 1 from 7, it will be 6. Sorry, 1 from 2, it will be 1. 1 from 5, it will be 4. Infinity minus 1 is infinity. So like that you have to do. Next time when you are reducing the minimum element from the column 2 or column B, if you find any 0 in that particular column or even in the particular row, whenever row wise column wise reduction is happening, if you find any 0, then there is no point of reducing, right? What reduce 0 you cannot reduce from anything, it will be same number. So if you find any 0 is available here, right? Here it is 0 is already there. While reducing the first row you got 0 here, 2 minus 2, 0. So in this column, what is the minimum value? 0 is the minimum value. So here you have reduced 1 here. 1 is the minimum, you done that. And then second column, it is, what is the value? 0 is already there, 0. So there is no reduction cost, 0 reduction cost. So what about this one? This also one 0 is there, this is also 0. What about this one? Here also one 0 is there, 0. So there is no reduction cost, only 1. So initially how much I reduced? 2 plus 4 plus 1 plus 4, which is 11. Row wise reduction, and column wise reduction it is 1. So 11 plus 1, 12 is the total reduction cost. 11 plus 1. So 12 is the final reduced cost, and this will be our final parent matrix, parent reduced matrix we will call it. It is very important matrix. First reduction happens. So this is the resulting matrix, which is infinity 3 1 0 0 infinity 1 2 5 infinity 3 5 infinity 0 and then 0 0 infinity. This is my resulting matrix, which is called M1. From here we will move further. What you should do now? So basically now you have started reducing the cost. Initial cost is 12. So you have started from A, vertex A, because I have started from A only, and you have done the initial reduction cost, which is 12. So all of you, so which are the chances? Like if you start from A, you can go to A, so we won't go because this is infinity. A to A, B to B, these all will ignore. A to B, A to C, A to D, this is all I can do. That salesperson can visit. Either he can visit A to B, or he can visit A to C, or he can visit A to D. So if you visit like that, so A to B, A to C, A to D, all of it. Here you write, because your first reduced cost is 12, so at the top of A you write 12. Now he is supposed to visit B, C, D. Okay. Based on that, which node he should visit, because first node created is B, second node created is D, third node is, okay. So we have to calculate all the cost. For B you have to calculate the cost, reduced cost. For C you have to calculate the cost. For D you have to calculate the reduced cost. So salesperson can visit either B or C or D. Initial calculation is 12. Okay. Now we need to calculate cost of traversing B, then C, then D. Okay. So let's say I'm trying to visit A to B. I'm trying to visit A to B. Okay. I have to find the cost. So as usual, this is my parent matrix, reduced parent matrix. This as it is, you write it here. As it is, write it here. Okay. Because I am visiting A to B, what you have to do, students, very important point. All A rows and B columns should be infinity. This parent matrix, change all A rows and B columns as infinity. That means this is infinity, this is infinity. Immediately you have to change this matrix. Not only that, if you do that, next you have to do, because A to B you are finding, so B to A also will be infinity. That means immediately put B to A. B to A also will be infinity. It will be heavy cost, B to A. Reversing back, B to A. These also you change to infinity. Remaining everything will remain same. All remaining things will remain same as it is, like parent matrix. These are the two things you have to consider. One is the A to B, because I am finding A to B, so A rows and B columns all should be infinity, and B to A also should be infinity. Remaining all will remain as it is, like parent matrix. Okay. Now again you have to do the reduction. Row wise, column wise reduction will happen. So row wise reduction, whenever there is all infinity, cost is 0. Whenever all entries is infinity, all entries, cost is 0. Otherwise here 1 0 is there, so 0 cost. You cannot subtract 0 from anything, right? Minimum is 0 in this row. Then third row also 0, 0 cost. Fourth row also 0, 0 cost. Now once you've done row wise reduction, column wise you check. A, this column, what is the minimum cost? 0, 0. Here also, to all infinity 0. This is also 0, this is also 0. So this is 0 cost, this is 0 cost. That means no reduction. Now A rows all infinity, B rows, B columns all infinity. Remaining values will be, but here B to A is also infinity, whichever I said, that is what. Okay. Next, if you do so, then I have to find, because the reduction cost is 0. Now what is the formula of calculating the cost every time with the help of a reduced matrix is that this cost, after reduction for any node, the total cost is CU comma V. That means in the parent matrix, whichever is the entry, that entry U comma V entry, plus reduced cost from the parent matrix reduced cost, plus currently whichever you have reduced, that will come. These three things will be added together. What are they? First is CU comma V, that means original entry in the parent matrix. Second is reduced cost, parent matrix, previous parent matrix, and plus currently calculated reduced cost So here how much currently calculated reduced cost? This one, students, 0. What is the parent matrix reduced cost? Just now we calculated 12. And what is the entry of C, A, comma B in the parent matrix? So parent matrix C, comma A, comma C entry is 3. A, comma C entry. See the formula C, U, comma V in the parent matrix. So what is A, comma B entry here? Entry is, A to B is entry 0, not 3. Plus parent matrix reduced cost, which is 12, plus the currently that you have reduced, which is how much? 0. This is 0, this is 0, altogether 0 you have reduced. So total altogether. So this is C, A, comma B is 0, plus 12 previously calculated reduced cost, plus 0, which is how much? Total 0 plus 12 plus 0, which is 12. Any doubt? Any doubt? So it is nothing but 12. A to B's cost is 12. But shall you stop here? We should not stop here. We should again calculate A to C, row A and column C. Because I am going to find A to C, this is my A to C. So immediately row A and column C, everything will be infinity. Correct? Then another extra thing is that which one should be infinity? C to A, very good. C to A will be infinity. Because I am going to find C to A to C, no? So A rows and C columns, everything is infinity that I have kept. C to A also will be immediately you have to do, otherwise if you forget this, your answers will differ, okay? And then remaining thing will remain as it is like parent matrix. Like which was the parent matrix that we have reduced initially, final reduction after 5. This M1, that's why I am saying M1 is important, because this whenever I calculated 12 here, which is 12, this is my parent node. This is important because you are moving from A to B, A to C, A to D. So A is important. A is what? Not the original matrix, the reduced matrix first, row and column both after reduction. So if you do all these things, so row wise tell me what is the reduction is going to happen. So what will be the cost here? What is the row wise reduction, students? What is the row wise reduction? Here it is 0. Yes or no? Tell me. All infinity is 0. Here 0 is row wise reduction is 0. Minimum entry you have to reduce from all the entries in the particular row. So row 2, what is the minimum value? 0. So 0 if you subtract, it is not going to do any change. So 0, there is no reduction cost. Here also it is 0, so 0. Here also it is 0, so 0 and infinity is 0. Okay? What about column wise? This is the reduced cost. Column wise, this is 0. This is 0. All infinity also 0. 0 infinity. Here also no reduction cost. When A to B also no reduction cost, 0 reduction. Currently reduced matrix is giving us 0 reducing cost. Okay. If it is the case, then you put the things in the formula. Check in the original matrix. What is the formula? Original matrix entry of A to C, because I am going to calculate A to C only. So what is the entry of A to C plus parent matrix cost plus recently calculated current matrix. So A to C entry I have to check in M1. A to C. What is the entry? 3. So previously calculated 12, 12 plus 3, currently reduced cost is 0. 12 plus 3 is 15. 15. So if you visit A to C, it will cost 15. So you write 15 here. 15 here. Now next only is remaining is A to D. A to D. You have to calculate A to D here. So this is now A to D, can you friends? A to D, parent matrix. That means all A entries and D entries will be infinity, and D to A also will be infinity. Then I will do row wise reduction and column wise reduction. So here if I do row wise reduction, you see all infinity, so 0. Here it is how much? Here how I will reduce? Second row, what is the minimum value? 3. 3 is the minimum value. This is what is the minimum value in this row. So 3 you have to subtract from 3, it is 0. Infinity minus 3 is infinity. 5 minus 3 is 2, infinity minus 3 is infinity. So 0, infinity, 2 infinity. What is the minimum cost here? 1. So 0, 0, 1 minus 1, 0, 1 minus 1, 0, infinity minus 1, infinity. So this is 1. What is the minimum cost? 0. So what is the total cost? 4. Column wise reduction, anything happening after reducing row? Column wise reduction, this is what? 0 is just a 0. Here also 0, already I got it 0. Here also 0. This is no column wise reduction, only row wise reduction, which is nothing but 4. Now what is the total cost? Parent matrix entry of C to D. Parent matrix entry of C to D, which is how much? C to D entry is 0. So that means what? That means sorry, C A to D. A to D, sorry, A to D, not C to D. A to D. So A to D entry is 5. So 5 plus 5 plus 12 plus 4, 16. I did some mistake. Yeah, that is 21, but it don't change. Okay, 21. This is 21. 21. Now up to this much, if you see all the values, which is 12, 15, 21, 3 methods could be utilized. One is FIFO branch and bound, one is LIFO branch and bound, another one is least cost branch and bound. Okay, so if I go with FIFO branch and bound, then which node will come, which node will be expanded first? B. If I go with LIFO branch and bound, which node will be expanded? D. And least cost branch and bound is again B. So that means here FIFO branch and bound and least cost branch and bound both are answering same. Okay, A to B. Now from here B, where are the locations you can go? You can go B to C, because B is the minimum, so we will expand this B. So this is 21. Okay, so we can go A to B, then B to C also I can go. B to C and B to D. A to B I have gone. From B where can I go? I can either go to C or go to D, because there is no other vertices. So if you go to C, if you go B to C, and this node will be expanded. Why? Because we are using least cost branch and bound. Least cost branch and bound. Whichever is the minimum cost, that means 12, that will be expanded. This is 15, this is 21. Whether these two will be expanded? No. Only this 12 wala will be expanded, because this is the minimum. Least cost. This is the least cost, so this will be expanded further. No more. Here this will be deleted. No more further expansion will happen for C and D. Only B. Okay. So B to C. So B to C means again you have to calculate B to C here. B to C. Calculate B to C. Again you do all B entries and C entries infinity. B entries and C entry, all B entry and C entries will be infinity, and so B entries and C entries all are infinity, and C to A also will be infinity. C to A also will be infinity. Okay, because starting vertex is A, C to A have to go. Reduce that. Now one thing is very clear. Now your parent matrix will change. Which will be your parent matrix? Not the M1. Which one? A to B wala parent matrix. That means now my parent matrix changes. What is my parent matrix now? I think I have already written. This one will be your parent matrix. Initial calculation. This is my M1, this is your M2. This is your parent matrix. A to B. A to B reduced wala matrix is your parent matrix. Okay? Now you have to refer this matrix, not the earlier matrix. Why? Because you have started expanding here B. Now if you do so, row wise reduction, column wise reduction, everything is 0, 0, no cost. So B to C entry you have to see in your parent matrix. So this is my parent matrix. B to C is how much? 5. So 5 plus 12, which is 17. Total cost. Then you have to do B to D also. This is 21. B to D also. B to D. And B to D also you have to do. B to D also entry will be how much? B to D, which is 13 if you calculate. It will be 13. Parent matrix, however, will be B matrix. Once you do that, then D to C also. So this is there. So this is 13 minimum. So you have to calculate B to C. You have calculate, which is 17. B to D also you have to calculate. So B to C you calculated 17. You have to also calculate B to D, which is, if you calculate, it will be 13. Now B to D, from D to where it can go again? D to C also it can go, na? D to C. So D to C also you have to calculate D to C. Now among these two nodes, which node will be expanded? This one or this one? D will be expanded because this is least cost branch and bound. Out of 17 and 13, 13 is minimum, so this will be expanded. D to C also is a chance. A to B has been visited, B to C, D has been visited. D to C, remaining cities, all cities it has to visit. All cities it has to visit. So if you go, then this is D to C. D to C, if you calculate, this is 13. 13. So D to C, which one will be parent matrix? Which one will be parent matrix? D matrix. That means whatever A to D you have calculated, B to D, this will be the parent matrix. Clear? This will be the parent matrix. Not this one. B to D, this one. This matrix will be the parent matrix. So once you do that, then this will be your final thing, and it will be like this only. So finally if you see which other nodes should be expanded, it has started with A, then it has visited to B, because these two are costly. This is 21, 15 this is, and this one is 12, right? Initial, and this is starting also 12, and this is 13. Sorry, this is 13, yeah, this is 13, this is also 13, I guess. 17. 13 and this is 13. I am asking what is the final path? Final path is this one, no? A to B, B to D, and D to C. This is your final path. So if you name it 1, 2, 3, 4, 5, 6, your path visited is 1, 2, 6, 7, and then 1.